Hey folks, welcome to chapter 18, Let There Be Light. So here we're going to be basically doing a review of the properties of light and then some introduction to spectroscopy and absorption of electromagnetic radiation in molecules and look at some Beer's law problems. Okay, so when we talk about the properties of light, I'm going to assume this is going to be a review for most of us, but we know that light can be described as both a wave and a particle. And so when we talk about light or electromagnetic radiation, right, we can talk about the wavelength of the light, the frequency is the number of oscillations per second. The wavelength is the distance across a wave. And there's relationships between all of these properties, right? So for electromagnetic radiation, which I might just be calling light from now on because that's the long name, but it's the same thing. This is for light. We have an equation, right? C is equal to nu times lambda, where nu is the frequency, and this would be typically in inverse seconds, which is hertz. Lambda would be wavelength, which would be given in a distance unit, maybe centimeters, nanometers, meters, something like that. And so we looked at if we were to multiply these, we would have a distance over time. So this would be speed. And in talking about electromagnetic radiation, specifically the speed of light, which has the constant c and has units of 2.998 times 10 to the 10 centimeters per second, or 8 meters per second. So, of course, this is just a relationship, so it can be rewritten. Oops. In multiple ways, right? You can solve for different parts of, or different properties of the light. So, this one is a fairly common way of writing it. We could say it's the speed times 1 over lambda, and 1 over lambda is called the wave number, and because it is given another symbol which is nu tilde, and we will define that here, wave number. And the reason it's written as nu tilde is proportional to frequency. So it's actually another way of saying frequency, but instead of having, say, units of per second, it would be units of maybe, say, per centimeter, right? And so that's called a wave number, and that's pretty commonly used in chemistry, in organic chemistry, in infrared spectroscopy, and things like that. So you'll see that one quite a bit. Okay, you probably also remember that energy is proportional to the frequency of the light, and this would be in the context of a photon, right, where we could say that the energy of a photon of a certain frequency of light is equal to h nu. E equals h nu. That's a good one to remember, where h is Planck's constant. I think there's a c in there. And this is equal to 6.626 times 10 to the negative 34 joules times seconds. H shows up a lot in physics. So we see some variations on a theme here. H is equal or equals H nu, or if we recall from the previous slide, we could say E is equals HC over lambda, or HC nu tilde, and these are all different ways of relating the photon energy to properties of the light. So looking at energy again, to kind of summarize this, we could say energy increases when frequency increases, or wave number increases, or wavelength decreases. And so we often see some sort of electromagnetic spectrum like the bottom here, where energy increases this way, right? As wavelength gets smaller, frequency goes up. We have this visible range, right? You've probably seen this many times, but what I want to make a connection to here is actually molecularly, atomically, chemically, what's happening on the molecular level at the same kinds of energies, right? So, like a photon of infrared light has energies in the 10 to the 12 to 10 to the 14 frequency hertz. And so what's happening is that a molecule actually vibrates at that same frequency. At really low energy, microwaves, molecules rotate at those frequencies. And then we have other kinds of higher energy processes. These will all come up in our next activity, which is actually molecular and atomic processes involved in spectroscopy. So I don't want to go into the detail of it here, but just know that that's why all of this matters to spectroscopy, why we care about properties of light, is that ultimately we're going to be relating the frequency, wavelength, and energy of photons to some sort of processes happening in the molecule, and thus maybe identifying what you have there. Okay, so that's where we're going, but for now we're going to focus on just kind of like the basics of spectroscopy, spectrophotometry, the absorption of light. There are some questions in the textbook that ask you to work through all the variations of these relationships, and so you can check those out if you would like. Okay, so let's talk about what happens with when light comes across our molecule. And this takes us to the start of section 18.2, the absorption of light. And we have here kind of like the simplest schematic representation of a spectrophotometer. And so we have, a light source, which is something that we can measure and quantify the light. We have some sort of wavelength selector where we pick one particular wavelength out of this whole spectrum. So this produces monochromatic light. Monochromatic is one color, basically, which we call P naught. The power of that would be P naught. It's going to interact with the sample. Something is going to happen. It's going to interact with it somehow. And the light that continues out is now impacted by whatever happened inside the sample, and we'll send that to a detector and determine the P power. Ultimately, this goes on somewhere to some sort of computer to either display the results or do some sort of analysis. So if we want to know the fraction of light that gets through the sample, which would be T, transmittance, we can look at P naught and P, and it's really just a ratio, right? It's going to be P over P naught. And it could be from 0, where none of the light gets through, to 1, where P is equal to P naught, all of the light gets through. Now, as you've seen before, T is not the easiest property to work with. It's actually not linear with some of the simple experimental parameters that we can control. And so a more useful quantity for chemical analysis is actually absorbance. Not absorption, which is like the phenomenon of what's happening, but absorbance. Absorbance is a quantity which is defined as A as the log of P naught over P, or the negative log of P over P naught, or actually the negative log of transmittance, right? So this can range from 0, right? When there's 100% transmittance, then there's 0 absorbance, right? But after that one, it's a little less intuitive because it's the log relationship. So if we look at like P over P naught would be a 1, right? The percent transmission would be 100%, and the absorbance would be 0. So what does an absorbance of 1 mean? Well, it doesn't mean that all of the light is absorbed, right? If T is only 10%, then the absorbance would be equal to 1, right? So if P over P naught 0.1, absorbance is equal to 1. So if we go by another factor of 10, where we have a 1% transmittance, the absorbance is 2. So this gives us kind of an idea of what these values correspond to in terms of light actually being absorbed. Okay, let's end here, and we'll come back in the next video and talk about Beer's law, which is the absorbance dependence on experimental parameters such as concentration and path length, and then also a chemical characteristic of the species doing the absorbance. So we'll come back for the next one, part 2.